I'm from Germany, Bavaria, south of Germany. And I work for the resource lab. So we're a lab of about 10 people, and we focus on a range of sustainability-related topics. Obviously, circular economy, waste management, also resilience, climate resilience. And for that, we use methods of industrial ecology, and I'll touch upon a few of them later on. And as Kamana already said, we've been working together for quite some time. And I'm really honored and humbled to be here because I think we can learn a lot from you, from Aloha Aina. And what has brought us together was somehow the idea of your ancestral, like historical ideas and like what's happening, especially policy-wise in Europe. And we saw that like both had its ups and downs, and we can really contribute to like the same goal by this exchange, by learning from each other. And kind of like our collaboration started, I'm gonna start today with just like giving a short overview of European policy on circular economy, but then mainly dive into some research findings from industrial ecology. So I'll give you some examples from what we did in our lab and what our learnings and challenges are. So what's Europe doing in general? And I'd say the most important thing is the European Green Deal. So the Green Deal is a set of policy initiatives, and it aims at making the economy climate neutral by 2050. So this is Europe's roadmap for a sustainable economy. And you see we have like a set of different components here. So I start somewhere down here. Imagine me pointing at it. So those initiatives target different things. For example, pollution. We already touched upon financing. So green financing is a big deal. And we have a taxonomy which identifies which activities of the economy have like a climate impact or which are in line with climate goals. And then we put in like mandatory reporting targets and mandatory reporting for a lot of those sectors. We have strategies like farm to fork, so we're targeting the agricultural aspects, we're targeting energy and mobility, and one major component, right here, is the transition to a circular economy. So right now, the EU needs a tremendous amount of materials, so we have a huge material footprint. And we need to decrease that footprint, and we need to increase our circular material use rate. So what we have is like an action plan, a kind of hands-on action plan for the circular economy. And I'll just give you a few insights here. So the aim is to change the way Europe consumes and produces. And we can only make that happen if we make it happen for people, regions, and cities. This means we need regionalized solutions and we need customized solutions. Just like we touched upon before, the circular economy needs to look different in different places. So there's quite a lot to it, but I'm going to point out the main focus areas. And the first focus area would be products. So we have, again, a set of, okay. Sorry, I have some animations in there, but I think it's a PDF, so we do not have the animations anymore. Okay, that's, yeah, products, so we're looking at the green point first. So the issue is that our products currently mainly are not made for circularity, and when we want to change that, we need to start at the design phase. So we're mainly targeting product design, but then also production processes. So our production processes are just too resource intensive at the time. And the other side are the consumers and also public buyers. So consumers might even be willing to adapt, but we need to empower them by maybe giving them a right to repair, by making spare parts available, by making access to repair available and affordable. And that's what targeted here. And the other major part is public procurement. So public procurement has 14% of, accounts for 14% of the gross domestic product in the EU, which means it's like a huge lever. So the EU set up targets for green procurement and also mandatory reporting on those green procurement goals here. And when I'm talking about products, I obviously mean like all kind of products, but again, here we have our key value chains. So the EU identified sectors which are resource intensive, You can see them here, like electronics, batteries, packaging, obviously plastics, construction, building, food and water. So we have resource-intensive sectors that also have a great potential to close the loop. So we have a great potential for circularity here. So those are our focus areas. And then the last focus area is waste reduction. So we have like what flows in on the one side, our products that are used, but then we have like still the entire issue of waste and waste management. And we do want to increase recycling. We're doing a lot about that, but we also want to make sure that what we do recycle is actually used again. So we're putting targets on the recycled content in products. So we want to make sure that recycled material is actually being reused again. And one really important thing is not even getting there, that we need to recycle so much. So we actually want to reduce waste at the source. So waste prevention. And that is now when I want to switch my focus a little bit into diving deeper into the research perspective and what waste management is about and waste reduction is about. So on the right side, you can see the waste hierarchy. So this is still some kind of policy. The waste hierarchy shows different waste management options and puts waste prevention at the very top. So it's kind of an upside-down pyramid. Meaning that the biggest volume and the highest priority should be on waste prevention, followed by reuse, recycling, and so on. And why is that? That's because the further we step down here, the more materials we lose. So every time we're like drawing a bigger circle, and like the closest circle is reuse because we keep materials at their same purpose, but at the bigger the cycle gets to recycling, to recovery, like burning things and recovering energy, the more materials we lose and the more energy we need to actually recover things. So that's why I want to focus on waste prevention. And to make that happen, we need a systemic action. So we cannot start at waste management if you want to prevent waste. We need to start way earlier. So we need to start at the design phase. And also a major point is we need to start at the habits of people. We need to start at the consumers, at the people producing, and at the people using our things. So we had another project here together with the German Ministry for Environment and Consumer Protection, and we developed guidelines for waste prevention. And already I mentioned about the importance of public procurement, so that's why we're targeting on local authorities here. And I put the link here because those guidelines are actually by now translated in English, so you could access them and actually understand them. What we did here is we worked on a document that facilitates setting up a waste prevention strategy. So this is kind of a blueprint on how to come up with your own waste prevention strategy, and it incorporates also a set of measures on what you could actually do to prevent waste. And this is just like a little snapshot out of it. So there are many more measures, but I want to focus on one thing. So you already see it highlighted here. It is the paper saving office. And we mean paper saving by means of digitalization. So the idea is we digitalize more, we need to print out less, we save paper. Sounds pretty logical to me. Well, but despite we do see an increase in digitalization, we do see that, but despite that, we do not see a decline in paper use. How does it come? Because I mean, that was the intention, right? So I just had a conversation like a few weeks ago with someone working at another German ministry, and he told me how digitalization works at their place. So they still do receive letters, and whenever they get a letter, that letter comes to the reception down there. So the people working at the reception then scans the document, throws away the original letter, and sends it via mail to the recipient. What does he do when he gets the mail? He prints it out so that he can take notes. Great, right? So we had like one letter in the first place, we're now having two. Like that was not the intention of it, not at all. This means, what I want to say here, first, we should have started way earlier along. So by printing out that very first letter, we already had like the first problem here. And then we didn't factor in the people. So we need to make the change in habits happen. And that's kind of a very good example of how the European circular economy is kind of top-down policy-driven. Like what I think we can very much learn from you as well is the community-based approach, like the bottom-up approach, like the will of the people to change things, to adapt, and that is what it's pretty much about. So we need to factor in the people, and we need to kind of get into the communities to their needs and then adapt to their needs to find solutions that actually work for the people. That would be, yeah, our first kind of insight and our first learning from waste prevention. If we now step down the waste hierarchy, we look at reuse. So we had a project here where we first of all identified the potential of reuse, like how much is there even that we could reuse? And for that, we looked at Bavarian collection points. And we found that for WEEE waste, so waste electrical and electronic equipment, we have 100,000 tons a year that could be reused in Bavaria alone, so just like the southern part of Germany, which is quite a lot. And about 66% of it are large appliances, so washing machines, freezers, refrigerators, and so on. So we're looking at those devices, and then we're thinking, well, reuse obviously has a high priority, but does it really make sense? Like, should we really reuse those old appliances when there are like way more efficient ones on the market? I mean, do we actually make it worse by using appliances which consume a lot of energy and water, or shouldn't we maybe opt for the newer, more efficient models? And that's what my second point is about. It's about taking kind of a life cycle perspective on things. So always thinking it through. And what we did then was we did actually calculations and implemented a reuse target for Germany. So we said, what would happen if we implement a 5% reuse target? That sounds like little, but we're currently reusing like 0.something%, so that is a big increase. And what would happen then? And then we modeled like everything that would happen from resource extraction to product manufacturing through the use phase into end of life. And then we combined what would happen if we have like more old reused appliances in the stock. They replace the new ones, so we need to manufacture less new ones. So what would it mean at the end of the day? And we found that we have like minor savings, like on average among different set of environmental impact categories, we have like 1% saving. So it's not a big deal, but it does not do any harm. So even for like, this is for the case of washing machines, which consume both water and energy. So even for those, we did have like little savings and we minimized waste. This is what it's still about. So they did not go like end of use. We could reuse them. So we minimized the waste. We have little savings. And also important, we found some kind of threshold. So 5% reuse would be fine because we assume that we're only using like 5% of the newer ones. But 100% reuse would not have been beneficial anymore. So we actually found limits to reuse. And this is what that point is about. So when we think about making decisions, we want those decisions, like political decisions, maybe putting in charge a reuse target. We need those decisions to be evidence-based. So we want to get the full picture. We want to take a look at the entire life cycle, make the decisions, know the limits to those targets, and then avoid any kind of burden shifting. So in that case, shifting burden from manufacturing to the use phase, which wouldn't do anything better. So taking a life cycle perspective and avoiding burden shifting was what that example is about. And then I have one last point to make, which is location shapes environmental impacts. So whenever we have human activity, we do have impacts. And it matters where this activity takes place. So human activity in one place can have different impacts than in another place. That means, obviously, the circular economy needs to be different in different places. And I have an example with me from a paper colleagues of mine wrote in my lab. And what you can see right here is a network for bioethanol generation in the EU. So we're talking about second generation bioethanol, which is made from residues, so mainly straw, so leftovers on the fields. And the idea is that this replaces petrol, obviously, and then also first generation bioethanol. So first generation is made out of sugar, starch. So here we have a competition with the food sector. And the green shades imply like how much residue is available. So the darker green, the more residues we have among Europe. And then the yellow cylinders show where we could actually install a biorefinery. So the residues are collected, brought there, and then their bioethanol is produced. So now where it's getting interesting. That's the next slide, actually. Oh no, that should look different. That should look very different. Well, imagine seeing the map you just saw with like the different fields, and okay, we just stick to the yellow cylinders, but I'm gonna cut it a little bit. So what we should see are like very different network designs here. So before here we had like, that is the maximum one. So that's the picture you would see here for global warming. And what we did was, this network, we optimized it for different objective functions, so with different goals, we optimized that network. And those different goals were first, on the left side, the blue one, the economic dimension. Then we optimized it for the environmental dimension and for the social one. And whatever we did, the outcome was very different. So what we see right here, that's how it looks like for the global warming potential. So if we optimize this network for global warming, we have like a very big network. So we're collecting everything that is available and building as much biorefineries as possible because we want to substitute all of that petrol. So we have a really huge network. If we optimize it economically, we would have those green areas only in Eastern Europe, so a really, really small network, because labor costs are rather low in Eastern European countries. So we had like a way smaller network. Whereas if you look at land use, which is also an environmental dimension, just a different objective, but both are environmental, we would have like a way smaller network and would only substitute first generation bioethanol. Because if you think only from a land use perspective, it doesn't make sense to do like bioethanol and substitute petrol, because petrol uses way less land. So again, different network design. And then we have a dimension we haven't even talked about, the entire social thing. So we looked at local employment. For local employment, it looked pretty much the same as for global warming, because the bigger the network, the more jobs, the better for this dimension. But for water use, again, we have a very small network where we only focus on areas with low water stress level. So what do I want to tell you with all of that? That's pretty much also what Kate touched upon. So what is it? What is it that makes people and regions thrive? So what is our goal? And we need to make sure to first figure out like what we want, what is it that makes people thriving, and then act accordingly. So that could look very different depending on what your objective is, what it is that makes people and regions thrive. And that is like the point I wanted to make with like that kind of slide you can see here. And then finally, what now? What does it mean for Hawaii? What does it mean for Oahu? And Kamana already gave an example at the very beginning. So we were at the ports, and I took that picture last Friday. And what you can see right here are about 1,000 containers. And those 1,000 containers came from that vessel you see back there. And that kind of vessel arrives 3 times a week. And from all of that that's arriving, 75% stays on the island. We already heard about the 500 cars, so that scales up. So 75% of those containers that arrive 3 times a week here stay on Oahu. So the question is, where does it go? I mean, it's not all food, it's not all consumed. It's a lot of consumer goods, it's electronics, it's furniture, it's everything. And how much more can the island actually take? And that's what our next research is going to focus on. So we want to like dive deeper into the material flows, what comes to the island, what stays, what leaves again, and then what is the most pressing issue? Like what is it, and how can we find solutions to make it hopefully more circular? Yeah, and this kind of gives the connection for my follow-up talk. So I'm talking about how much can stay. So this is about material stocks, and then also the risks that come with that. Thank you very much.
Thank you, Kamana. Thank you, University of Hawaii, for having us all here at the panel. This is really exciting times on this island, and I would love to share some of my thoughts and my long-term research. So, as you can see, the title is trying to make a case, why do we need an island circular economy? And I will talk about insights from socio-metabolic research, and I will explain in a bit what that is. So the formatting has changed, as we already learned from earlier. but islands are sites of multi-hazard risk and cascades, as we heard already early this morning. And this figure, you can see that there are multiple risks and hazards, how they are interconnected with unpleasant feedback loops. And this is primarily due to the tight coupling of socio-ecological systems on islands because of their smallness and also boundedness. And so what happens is that even small or single events can put in motion a series of risks and cascades that can move towards a system collapse over time. So tipping points can be reached very rapidly on small islands. And for example, you see the fires that were experienced here not too far away. I see this as a tipping point that was a consequence of previous land use kind of decisions that were made. And so based on that, you can see cascade. And for me, like the way I would see that is fires were a tipping point, and which could lead to further cascade impacts. And that could affect ecosystems, the marine system, livelihoods, also soil and biodiversity and so on. So we want to understand islands as very sensitive, very fragile, but also very dynamic kind of systems. But the good news is that positive tipping points can also be reached as say rapidly if there is a political will. And so things don't always have to go downwards, but they can also go upwards. So there is the hope there. So islands are like living organisms. So I'm going to compare living organisms with islands from a metabolic perspective. So this animation is not going to work, but just imagine the arrows flying from left to right. So they would normally fly to as you can say that like a cow would consume, biomass, water, air, and then it would metabolize these resources, and there would be outflows, which would be milk products or waste. So similarly, island systems also metabolize resources. They extract resources, prime resources, or they would import them. They would metabolize, and there would be an outflow. There would be waste. There would be exports. Some of those flows stay on the island. In fact, a significant amount of flows stay in the socioeconomic system, which we can say they're converted into stocks. And you will hear more about stocks from the next speaker, Hiroki. Stocks, when I'm referring to stocks, it means more kind of infrastructure, buildings. So that is like the university, like roads, housing. So anything that stays in the system for longer than a year, we consider them as a stock. So other stocks are also like durables, like machineries and cars. As we learn, so many cars arrive every day, they become a stock on the island. And they stay longer than a year, and over time, there are outflows. And the function of these stocks clearly is they give you critical societal services. So when you build a road, it's giving you a service for transport. When you build a university, it's giving you education service. When you're building, a treatment, waste treatment plant, it's giving you a sanitation service. So you have different services associated with those stocks. So in this sense, we can say that socio-metabolic flows, they create, operate, and maintain society's material stocks that provide then kind of critical services to society. So in industrial ecology field, we can actually quantify all these arrows that you see here. These can be quantified by different methods, materials, and stock flow analysis. And so, and I won't go into the details of the methods, but there's a whole kind of toolkit and a suite of methods. So to make things simple, it's basically, this is what it is, It's there's an input, there's a put, and there is an output. So, but the only thing is that only 25% of the global inputs become outputs within a year. So it is incredible. Like, this is a very interesting number to know, and that's why the talk of Hiroki is really very, very important as well, to talk about what stays in the stocks. So what he's saying is that 75% of global material extraction every year that we extract each year globally goes either into building new stocks, infrastructure, buildings, or to operate it or to maintain them. So you can imagine the significant amount of resources that we extract just for stocks to provide services. And in 1900, this number was 20%. So this is rising, as you can see. So how did that happen? So I want to tell you about a kind of dynamic system that is at work behind. So as economies develop, when they generate wealth, they stimulate the demand for essential services. So you need better housing, better roads, you need better healthcare, better transport systems. So, and you only can deliver that through building of stocks, infrastructure. And that requires flows. So the two pictures you see is Male. This is the capital of the Maldives. You can see the amount of stocks that were there in like 50 years ago, and now you see it's total concrete. So obviously the stocks are influencing the flows. You need more flows to operate and maintain that infrastructure. So there is this kind of a system. This was cut out anyhow, but so there's a dynamic feedback loop called a lock-in effect, And so the decisions we make today on what buildings or what infrastructure to build and what design should that be, or what type, what materials to use, will actually determine future resource flows. So you get into a lock-in effect where this drives the whole system. The most demand for services needs more flows, like more mining, more construction material, then more stocks. So it goes in this feedback system, which over time, you are creating risk over time in the system. So just like, imagine like a human body, our metabolism, you go to a doctor and the doctor says, well, my friend, your metabolism is not very good, and you have a few options here. So you can either change to a healthy metabolism, eat healthy food, stop smoking or whatever, do more exercise, or you can take this type of medicines and have it for the rest of your life so you can manage the risk in the future, because you have a chance of heart attack, in 10 years as you go. So, doctors can read let's say the signals or from tests and predict the risks, the future risks to your health in the future. So similarly, you will see that the metabolism of socioeconomic systems or islands also then embody certain risks based on their resource use patterns. And over time, as you can see, this cascade can go into tipping point and collapse. So to summarize, what is social metabolic risk? This is to islands just like circulatory health problems are to humans. They both constrain the entity's ability to withstand shocks and changes. So if you have a weak metabolism, you are more vulnerable and prone to disease and changes in the environment, right? So, but if you are more healthy metabolism, you can resist shocks. So we find a lot of maladaptive and climate insensitive development on islands, unfortunately, and such as coastal squeeze, and Hawaii is no, you can say exception to that. High import dependency, we talked about this today, undiversified exports to single like tourism or certain type of crops, centralized energy systems. All these kind of maladaptive practices, they can magnify the island's climate and economic vulnerability when there's a pandemic or there's a hurricane, any kind of disruptions in supply chains. So that can all be very disruptive to the entire system. So I will skip this. This is basically my program called the Metabolism of Islands. And so we have a team of people, we work on different projects across the world, different islands, and this is what we try to look at. The risks, we look at the collapse potential. We look from linear to circular metabolism, how one can transition. We also look at the stock flow service nexus. So I want to give you just two examples to wrap this up from the Caribbean. And I'm happy to provide and talk more about the other examples as well, but they're very similar patterns. So this is Grenada. And we see here, one example is the map of Grenada. You see the red hotspots where they are. This is the concentration of infrastructure, of stocks, the material stocks. You can see there's a coastal squeeze here. There's a bias towards building in the southwest of the island. Now, this is also exposed to hurricanes, this area. So it's not rocket science to tell what happens to this infrastructure when there is an extreme event. At the same time, you can see the certain different sectors that are exposed, to risk, and also the distribution, like stocks and also services. So we did a simple calculation. We did several calculations, but here just one example is 1 meter sea level rise scenario. So you can see tourism infrastructure is is highly exposed, so at high risk. And then industrial and residential, and you can see the amount of material stocks that are exposed to only 1 meter sea level rise. And this is not counting when there are extreme events. This goes even more devastating. Like, for example, you see the material flows of this. So these are construction materials you can see over time, and you see spikes, right? It's very unusual to see spikes in the material flow over time when you look at other places. These spikes represents building, reconstruction and destruction. It's kind of cycles. So the highest spike there is when there was a hurricane. So you would have to import materials, rebuild, and then there is a disaster waste that is there, stays on the islands, and you have to dump it somewhere. So the Bahamas, very similarly, you see that with 1 meter sea level rise, the northern part of the island is highly exposed, and transport infrastructure is the most at risk. So airports around 12%, seaports around 39% at risk with the modest sea level rise scenario. And we don't have to wait for that 1 meter sea level rise to happen. This was also animated. I didn't want to show you the whole thing. Just the top part is that there was the oil, because Bahamas imports most of its oil and it's stored at the port somewhere. So when in 2019 there was a Hurricane Dorian, there was oil spill because the facilities were actually destroyed. So suddenly that creates a cascade of other types of risks. So a lot of oil in the ocean, and damage to ecosystems, the marine systems, and also to the entire energy system. So you can see the kind of cascades that can build up when we are thinking of a certain type of metabolism. So Bahamas, like many other islands, have very, very little amount of recycling. And what I want to point down, so this is a material flow like over time. Like in 2018, you see how much throughput that takes place from imports, domestic extraction, but the figure is only less than 1% is actually recycled in the Bahamas. And this is pretty much, in most islands we have looked at, this is less than 1%. While the global recycling rate is now 7.2%, I think, which is not great either, 7.2%, and this is less than 1%. So we look at this island where we are, so this is data from 2006. You see that this is also less than 1% recycling here on this island. And on the other hand, the amount of waste being generated has only increased. So in 2006, it was 1.8 million tons of waste being generated on this island, and now it is 2.2 million tons. So this is outgrowing the population growth even, so waste is growing faster than population growth. So just 500,000 tons is increased in 15 years. So 1/3 is construction and demolition waste, while other is the solid municipal waste. And there is high import dependency and so things that we talked about earlier. While most of the materials that arrive here stay on the island, like because containers are going back empty. Landfill capacity is at its limits, so what's next? And that's the big question. So the problem is it's just too much put. So for me, the high leverage is that we have to tackle the put, because the put determines the input and the output. You see, oftentimes circular economy is always seen, okay, let's talk about the waste, let's recycle it, reuse it. So we are so focused on the waste that, again, going back to the hierarchy that also Sandra was talking about, how can you reduce the waste, And so the put is high leverage here. So we need some strategies, and this is maybe very much aligns with the Aloha Aina kind of circular economy principles. We call it the 5E strategies. I just built it up, don't worry about it, it's nothing. So one is towards, so you evolve towards circular economy, but not on a product level or on a single sector level, really on a system level. Like Kate earlier talked about, you're not interested in your cell phone, donut, or a single, look at the system, right? We're really interested in systems. So the first thing is really evolve towards a circular economy at the system level. That's very important. And increase the localization of some sectors like food, energy, construction materials. Expand principles to the island economy. So well-being contributions, how can you achieve a high quality of life at the lowest environmental impact? And so what is that sweet spot? And that's what, again, with the donut that, Kate was showing that what is that sweet spot? Nobody's in there, right? On the top left. So that's the sweet spot we want to get to. Then again, going back to the ancestral circular economy principles is how can we draw more on nature-based solutions, more on not working against nature, but living with nature, building with nature to provide crucial societal services. And then the issue of justice is very important, that we need to ensure that the cost and benefit of social metabolism or island metabolism is equally distributed. Shouldn't be that some people benefit from the metabolism and others pay the price of that metabolism, so which is often the case. So that's the equity lens to it. But again, if you're going on your next beach holiday, please take a look at more readings. So, so I didn't have time to cover all the work, but here you go. And this is an open access book that you can look. It's really, you can read this volume, and take it with you. So thank you again, and thank you for listening.
It is my very first time in my life to have lots of leaf on my neck. Yeah, it's a really lovely situation. Thank you very much, Kamara. It's really lovely. And also I'm the put guy. Yeah. So we are much very focusing on the put, the research for last 20 years. So I want to show you more about the research activities and also our put result things. Before we are starting that, I want to show our 3 key messages of my talk today. The first thing is that we should, that's 3 key messages. I hope you do have several ideas from our talk about this one. The first thing is about that we should consider the resource use as well as energy consumption and CO2 emission and also climate change issues. And in longer durability, the product that leads to establishing the sustainable stock-based society, not flow-based society. And stock-based society that contribute to reducing TMR, I'll talk you later, and also the landfill and CO2 emission, and reduce, reuse, recycling things that should be the set with a longer lifespan of the product. Well, that's my key message. But in short, design, that is very important to think about. So design for generations and also use for generations. That is quite important idea. I take the photo from our building of my office, and this is the scape of the Nagoya. I took this photo to the west side, to the east side. So I hope this animation work well, but oh yes, work well. So from the east, west side of the Nagoya to look into the east side of the Nagoya. And then maybe you could see, this is a very green area is our campus, but if you see more in detail for the, this is the west side, west side. The west side, that is the city center. There is some Nagoya station, which is Shinkansen train, that the Subaru train stopped there. And this is one of the most dense area of the Nagoya city. And our very basic research question is how much materials we need for our life. How much materials we need for our life. It's Simron is also talking about our metabolism of the body, that the same things, how much materials for our body, how much put in there. how much put, and how much output. So that's the question for the city. So we try to count, we try to measure the weight of the city for many years. So why we are doing like that? But that is, for myself, that is a very simple academic questions. But think about, I'm actually another side of my work is for environmental something system analysis and a kind of the professors of the university or something. So then I need to have more academic questions. So that is the one of my friends in the University of Kassel who names Stefan Bringel to give me the very clear answer. Every kilogram of the material we use comes with the environmental impact. So that's one of the very important word. And as Simon said, we are using lots of buildings and roadways and lots of infrastructures that is supporting our life and industrial activities. But basically the very essential service from the material stock, kind of the buildings and roadways and some things, and this supporting our life and also the industry. That is as Simon says, stock flows, stock service linkage. Then we have the materials flow of energy and also the material flow, it's the resource flow. That is kind of the material flow and also the material stock relationship. That we are saying that the metabolism of the society. So think about Stefan's words, that every kilogram of material we use comes with environmental impact. I pick up one photo which I took in Philippines, the one of the island names Butuan, Mindanao Island, Butuan City. Do you know what, this is kind of the metal ore, but do you know what kind of the metal ore is, you guess? Iron, yes, close. Yeah. It's close, but this is nickel. Nickel. So maybe nickel is the very familiar metal that maybe used to be in your pocket. There's a lot of nickel in there. Yeah, 5 cents of the coin of the United States is, I heard 25% is the nickel. But think about to having this nickel ore. Of course, we have the nickel mine. This is the nickel mine. The nickel exists almost like a 10 to 20, 30 meters depth from the ground. So the miner is shaping the ground. And they cut everything like this. And most of the nickel is gone. And then there's some rehabilitation of the ground to put a lot of the trees. But just after shaving the ground, of course, there's a very big environmental impact like this. There's no rain at the time, but there is a water flow from the river that is the link to the beautiful ocean. Look like this. A kilometer long, contaminated by the eroded soil, and also the very much big effect to the corals and also the sea environment as well, ocean environment as well. But not only that, the shaped ground, and after shaping the ground, they are putting the lots of trees, but to rehabilitate all the ecosystem of the original forest, it takes many, many years after the deforestation. So it has lots of environmental impact behind we are using the 5 cents of the coin, right? So for example, the nickel things, if you want to have a 1 kilogram of nickel, you need to excavate, and also you need to move some soil or something. That in total, you need to have 260 kilogram for 1 kilogram of nickel. So it's a quite huge of the backside of the story of using the nickel, right? So not only the nickel. So for example, like this is the steel production system. The nickel is mainly used for the stainless steel, but the think about the production of steel is also same. I skipped a very small process, but if you want to use the 1 tons of steel, it's also, you need to kind of something like excavate and the soil erodes these things. It's in total, it's almost like 10 tons of something related to the materials is moving somewhere else. That is, we are saying TMR, total material requirement. That's that it's very important to thinking about of the backside of the material flows, and also the usage of the material flows. Of course, the CO2 emission in the whole process of the steel is there's some emission there, but there's not many people is focusing on what's the backside of the total material flows of our activities. Same things for the cement production. This is a limestone mine in Japan. There's some cement production systems, but the same things. If we have the 1 tons of Portland cement, there is 5.8 tons of some things is not consumed, but there's some relationship to moving somewhere else, right? That's the excavation process as well. And the CO2 is 0.84 tons for the 1 tons of Portland cement. So that we need to thinking about at the same time of CO2 emission and also the TMR idea. So that TMR idea, that as I said, the nickel is 1 kilogram of nickel is equal to the 260 kilogram of the backside of the something related to the environmental impact. And the steel, as I said, is a 10 kilogram of TMR per kilogram. And plastics is almost same. And the aluminum is 50 kilogram, copper 400 kilograms, and gold, maybe on your ring, is almost 1 million times of the TMRs of your rings. So maybe you will ask by someone how much the rings weight of yours. And then maybe you can answer clearly, million times. Yeah. So that's the thing. So the every kilogram of the material we use comes with the environmental impact. And so that's why we are doing lots of things that for counting how much material we use by using the many technologies. For example, like one of the useful things, recent useful things is the GIS data. That we are creating the kind of the 3D shaped GIS data for many cities in the world. Hopefully, maybe next challenge will be the Honolulu or something together with Hawaiʻi universities as well. And I bring here the one of the example of our 4D databases or 4D GIS databases. We said 3D databases with time series. We said 4D GIS databases. We are picking up the one of the example in Nagoya. That is in the city center of Nagoya. There is some castle, one of the shogunate families' castle there, and also the left-hand side is Nagoya Station, which I sent in the last picture. That is there, and also the just south of the castle area, there is the big commercial area of the Nagoya area. So we create this city model from the 1960, the almost 60 years data. So this is the 1960s scape of our Nagoya city center. That's I put the color on the red is steel-based building, and the blue, light blue, is reinforced concrete building, and the green one is a wooden-based building. So I'll make some animation, but you can see change of the colors of these cities. So this is 1960, 1970, 80, 90, 1997, 2003, and 9, and this is 16 and 20. So you know the change of the colors. That means change the shape of the buildings and increasing the capacity of the space of the cities, and that cause the change of the structures. That change of the structure cause the use of materials is changed, need lots of cement and concrete, and also need lots of aluminum and steel, and of course nickel as well. So, but behind the production, we have lots of TMR to having some service from the city. So that's the idea of using kind of the historical change of the databases with a 3D database. So we want to know more about the whole countries. We are doing something like cities, GIS databases for whole country. We are counting every single building of Japan and every single roadway of Japan by using some GIS databases. That takes almost like 2 weeks for the fastest machine in my lab. So that's almost like 26 billion tons only for buildings. That's almost like 150 or something per person. But at the time of the 2010, we have something like these buildings in the whole country as a material stock. And the same things about the infrastructure. We make some in the infrastructure just 4D databases from the 1960, from the 2020. So and then we have a lot of discussion with the Ministry of Environment of Japan. The Ministry of Environment is only have the material flow figure and also material flow indicator systems, not stock indicator system. So we are trying to introduce stock-based indicator is really good support to the flow-based indicator. So we are trying to make the whole kind of the picture of the material flow of Japan based on the kind of the GIS work. This is the historical change from the 1990 to 2015, the change of the material flow and change of the material stock. So like input, output, right? So the input is, as you see, the shrinking. And put is increasing a lot, no decreasing. But output is slightly decreasing. But recycling is also slightly increasing. So that's the picture of the whole Japan's the input, output, right? So that's the things. So think about the material stock. In 1990, in the whole country of Japan, is 140 tons per person. But in 2015, we have the 250 tons per person. 250 tons per person we need for having some life in Japan. But of course, think about the nickel is 100 times more of the TMR, and something like another metal is more than the 100 times of the TMR. So behind that kind of the whole metabolism, we have lots of things of the environmental impact to think about, not only our sustainability, but for the global sustainability is need to think about with the TMR idea. So, sorry, I skipped this. And we are doing some the global work as well. Based on our global work, we identified, this is 2010 data, but the graph is, the vertical axis is the tons per person. And the horizontal axis is almost like, this is the year. And if you see the gray line, that is the industrial average of the material stock. That is almost like 320 tons per person is the industrial countries average. United States, the mainland continent area of the United States is almost like 370 tons per person. But maybe Hawaii is much dense area, so that I think it's much smaller, close to Japan as well. So Japan is almost like 300 per person at the time. That is including the infrastructure and also the many things for the person as well. Right, and also we are doing the lots of things for the estimating for the future. Every scenario we use, it's very difficult to reduce the total material stock per person. So maybe we keep accumulating our stock, but maybe we need to find, as Simon said, we need to saturate or we need to reduce or we need to slim the things as well. Okay, so then I want to conclude again. This is a little bit more. This is our kind of another the product of the almost 10 years ago. We have the big tsunami in the Tohoku area in the north part of Japan. After the big tsunamis, we asked by the Ministry of Environment to count the material stock of the tsunami invaded area. That is very much similar to the total amount of the roasted material stock of that area. So that is also the byproduct of what we are doing for the tsunami things as well. But I think that is kind of very good to know about think about the adaptation option of the climate change can prevent kind of the roasting the material stock in the future. So again, too much slide, sorry. That's the too longer material stock society. We need to have lots of accumulation of the capital beyond the generation. Not like flow-based society. The flow-based societies keep rebuilding and keep producing the material stock for every generations. So that we want to keep our capital to our next generation. So that means we want to have so much accumulation of some capital beyond the generations. Okay, so back to my key message. I hope you have lots of idea related to this. Okay, and again, the design for the generation and also use for generation is quite important to think about sustainability things. Mahalo nui loa. Thank you very much.
We can kind of see some of the tools that are being used in other places in the world and think about their applicability for our own island. So thank you, folks, for this incredible work and partnership. Thank you for all the fellowship and sharing. Do I see? Yes, Amy.
I'm not sure. Oh, it is on.
Sorry, Representative Peruso. Yes,
Amy.
excuse me.
So I had a question for Haruki. When you were doing, is almost one of your last slides, and you're doing global analysis. I was wondering if you were also taking into account military production. Okay. So all of this is non-military production.
I think so. Yeah, I think so. Means that is very based on statistic data. So that some military things is not on the statistic data. So that's why I think some of the materials is included because we have the statistic data from the production side. That is some of it is included, but maybe some of the stock analysis is not counted because of the maybe military things as well. Yeah.
Okay, thank you.
Thank you.
Sorry, and a follow-up on that, Amy, in our own building blocks for our material flow analysis, we've already identified, we're not going to get data from Pearl Harbor Port. So any material flow analysis we look at for Honolulu is going to be underestimated because of that. Yep. Other questions? I saw in the front, your hand.
All of you were fantastic, but again, for Rocky, that based on your material flow analysis, does it lead you to a recommendation about different types of materials to be used for building and infrastructure that would be less resource intensive?
Yes, thank you very much. That's a very important question. We try to estimate some kind of some TMR with many materials to be the substitute of for example, like concrete piles or some things. For example, like very recently, we have a lot of technology with wooden pillar that instead of the concrete pillar. That is sometimes it's much lower TMR, but of course we have a lot of controversy issues. Sometimes fires, sometimes against the shaking. Especially in Japan, we have lots of earthquake, so we have the shaking issues and shaking issues as well. So there's kind of the lots of, if we clear the lots of conditions, we can provide some TMR data for substitute material for that. Yeah, thank you.
Just a follow-up on that. What about the urban mine concept? In terms of the urban mine. So so instead of re-extracting, do you want to? Yeah.
Yeah, that is also the urban mine is a quite important idea because we have the historical change of the material stock spatially. So that is spatial data analysis can tell where is the old steel, where the old nickel is there. Then maybe that if that building is demolished, then maybe it's very easy to find how much materials, how much nickel from there, how much steel from there, and how much wood from there or something. And then it's very exact idea of the urban mining.
Thank you. Sorry, last question, and then we'll transition to our next panel.
Thanks. I wanted to ask the question about many times stock increases happen because of government's decision for economic stimulus. So building highways, building freeways, renovating buildings. How do we address that when we need to keep people employed and those kinds of things when we're looking at this overall pluses and minuses?
Okay, this is the example of Japan, but it's very much related to the property tax system of Japan. That is a Japanese story, but if you build up the house, that's the property tax is 100% in the several years after building. And after that, they are reducing until the 30 years. After 30 years, it's going to be zero for the part of the property, the building taxes. So everybody don't want to have much longer the building. So the companies, they want to have some buildings with the tax, how can I say?
Tax-free.
Yeah, tax-free things as well. So they want to keep buildings with the shorter lifespan buildings. So we need to convince to the government tax systems to have much longer the stock-based societies buildings as well. Yeah, it's quite important.
Yeah, and can I make a comment on that? So I think the other part of keeping people employed is these concepts like urban mine. So we could rebuild stocks, but if we're taking stocks that aren't out of Mother Earth again, and we're reusing them, we're employing people to revitalize and reutilize those stocks. So we're still keeping people employed, but limiting the environmental degradation. But yeah.
We also visited Reuse Hawaii just like a few days ago, which are a great example of like how you can generate jobs, actually taking things apart, keeping materials at the highest value, and then repurposing it for making buildings. So that like is employment, they generate revenue, they use materials. Great, like, it's like non-profit, it is.
Yes,
right? Yeah,
yes. And I think they're here if you want to talk story with Reuse Hawaii. Somebody raise their hands. Yeah, okay. But again, more conversations in the reception if you folks like. We're going to transition to our next panel, but I just want to again mahalo each of you for your work and being here and fellowship. So like Kate, there's more work to come for all of us, but this is a great intervention and start today.